Hello there, welcome to Everything Polar Coordinates Level 3. Just as in the other two videos, I'm going to be talking specifically about polar coordinates, but trying to generalize the ideas I discuss to apply to any other coordinate system. So in this video, we're going to be exploring how to formulate the del or Nabla operator in polar coordinates. This is an extremely useful operator, that comes up all the time in physics. And we'll go ahead and discuss how we can actually come up with this. But we need to build up to it first. I can't just introduce Nabla without talking about the notion of a scalar field and the notion of a vector field. Okay, so a scalar field, these are very easy to understand, right? A scalar field is simply a function that assigns a scalar number to every point in our Euclidean space, and a vector field just assigns a vector to every point in Euclidean space, right? And we can see that the notation here, is very suggestive of that, right? I'm saying that I have some scalar function here as a function of, some position vector in my space, right? So my position vector is going to point somewhere, and then I'm going to get some scalar value at that location. And then same deal for a vector field. At every position, we're going to be putting down some vector. So before I go any deeper, what I want to get across is that the Nabla operator is basically the analogy to the derivative, right? Derivative we would just apply to a one-dimensional function. The Nabla is analogous to that for these more general ideas of scalar fields and vector fields, right? And it's going to allow us to discuss notions of rate of change in multiple dimensions. But so bear in mind that it's useful when talking about both scalar fields and vector fields. In this video where I'm trying to formulate Nabla, and I need to keep this focused, so I'm really just going to focus on scalar fields for this video, right? But bear in mind that we're creating an operator that is extremely useful for both scalar and vector fields, okay? But I need to keep things focused and to the point. So let's go ahead and talk a little bit about visualizing scalar fields. So for the function that I'm going to be talking about in this video, I'm specifically going to be talking about T, temperature. Nice and easy, nice and physical, easy to understand. Okay, so here I have some function, temperature, as a function of my position, right? And probably what we're used to is seeing, a graph like this where we dedicate one axis to position and then we dedicate an axis to our temperature. The problem with this, right? The problem with this is that we're needing this extra dimension here to plot out our temperature. We're putting our x-axis here, and then we're putting our temperature down in a separate axis. But obviously if we live in 3D space, right, and we have x, y, and z coordinates, we're already taking up 3 dimensions, right? We can't really dedicate a 4th axis to, plotting that function, right? So we can kind of more intuitively see this and more match this up with physical reality, right? If we just introduce, a function kind of like this, right? Where t of x here is just indicated by the colors along the rod, right? So over here towards the center of the rod, it's, obviously this is corresponding over here. The rod is very cold. And then as we move more towards the outer parts of the rod, we're seeing that the rod is, getting hotter, it's heating up. So we can use these kinds of heat maps or color maps to help us visualize these scalar fields. And of course, this is going to be extremely useful once we start talking about things in higher dimensions, right? The other thing that I want to detach us from just a little bit is, in this top picture, we would very easily define the derivative, dt dx, at some point, let's go ahead and say, at some point p, this would be the slope of the tangent line, right? Tangent line through p, which is great, right? Although down here, once we start introducing just the notion of a scalar field, right, so down here, we don't really have that same literal geometric interpretation of the slope of a tangent line because, well, we don't really have anything to make a slope out of anymore. But, we can still very easily resolve this just using a rate of change definition. So if here's point P, we can still use the derivative to define just the local rate of change, right? The local rate of change of our scalar field, right? Still behaving exactly the same. I'm just trying to detach us a little bit from this notion of needing to have this geometric slope all the time, right? Because, well, we don't really have a curve to make a slope out of. All right, now with that 1D warm-up, we're finally ready to talk about, the temperature of a sheet. Now we're going into 2D, right? And now we can finally start talking a little bit about polar coordinates again, right? So obviously kind of, the analogy here that I'm trying to make is before we were talking about the derivative at some point P, all right? And now, right, let's go ahead and introduce a point P here on this sheet, some arbitrary point P, right? We're going to have to think a little bit harder about what the quote-unquote derivative is here, right? What describes the local rate of change over my scalar field at this, location P, right? Because obviously in the 1D example, there's really only one way that you can move. You can move, to the right or to the left. And we define the derivative when you have a positive displacement, right? Right, but now there's some ambiguity here when we go up to 2D. Now I could move potentially in any direction out from point P. I could move out, any of these, 360 degrees. So which direction am I moving out to describe the quote-unquote local rate of change of my scalar field? And I think I'll be able to make this really clear if I go back to the temperature of the rod, right? So in other words, okay, so if I take the derivative dt dx at some location P, right? And now I multiply this by dx, right? This is really just going to give me back the infinitesimal change in my temperature dt at that point, right? And this is kind of an infinitesimal version of, the fundamental theorem of calculus, right? That if you gave me instead 2 points, right? I'll go ahead and call them P and Q, integral from P to Q of dt dx, then this is going to give me, the delta t at point Q minus t at point P. This is going to give me my delta t between my points. All right, so back over to the second picture here. Now I'm going to go ahead and introduce an infinitesimal displacement vector dr. Totally analogous to dx here, but it's just pointing in some arbitrary direction now. Right, and now hopefully the analogy is clear. I need some operator working on t, and we evaluate it at this location P, and then we have some kind of multiplication, right, in the dr direction that's going to give us the infinitesimal change in temperature. That's exactly what we want. We want that exact analogy to the 1D scenario, right? Such that if I were to integrate this, right, between 2 points, P and Q, right, I would ultimately get, again, a delta, t at point Q minus t at point P, right? That's exactly what we're looking for. All right, now there's 2 things that we definitely know before we really do much. We can just think about this very briefly. The first thing is that this Nabla operator, when it operates on t, has to be a vector quantity, okay? And the reason why it has to be a vector quantity, there's a couple ways you could justify this. The first is that you can't take a scalar and multiply it by a vector and output a scalar, right? A scalar is just going to scale up another vector. It's not going to output a scalar. So that's issue 1 if we were to propose that this guy was a scalar. And then issue number 2, it just related to common sense, which is probably if we want to describe rates of change very generally, we're going to want to describe rates of change in multiple directions, right? In multiple independent directions, Okay, so that's kind of a looser justification, but you could definitely justify it, in the first way that I said. Right, and this little package here, also known as the gradient, right, if it's containing all of the information, right, about the rates of change of t in each independent direction, what we really want to do is we want to project that in a particular direction dr, right? And we have an operator that does just that. It's called the dot product, okay? It's called the dot product. Okay, and I use the term project a little bit loosely, right? Really, projections only happen when you, take a dot product with a unit vector, but it's still the same idea. It's going to find the similarity, right, in this gradient of t applied in the direction dr. That's exactly what we're going for. So the takeaway message here is that this is how we ultimately define the gradient operator. This is a very good way to define the gradient operator, with the context of scalar fields. And this guy down here is referred to as the fundamental theorem of gradients. And now with this definition, we're finally ready to actually determine what the Nabla operator looks like in our coordinate system. Okay? So here's our little 3-step program to determine Nabla. So first, we're going to rewrite dr in terms of our coordinates tangent basis vectors, which we already came up with the tangent basis vectors for polar coordinates in the last video. Great. Next, we're going to expand dt out with the multivariable chain rule, and then from there, we're just going to be able to read off Nabla. Very, very easy, and we'll go through each of these steps. So first, let's go ahead and determine dr for our coordinate system, right? So in other words, let's go ahead and write this out. Let's go ahead and say that here we are. I'm back in Euclidean space. I can go ahead and define two position vectors, right? So here's going to be position vector r, right? And here I'm going to introduce, a position vector r plus dr, right? And these are going to be, there's going to be a displacement between these vectors dr, right? And in polar coordinates, we've discussed all of this already. Our position vector is simply going to be equal to some radial component r in the r hat direction, where r hat is our polar unit vector. So, right, and I talked about these before. Let me go ahead and write these down. Here's our r hat unit vector. Here's our theta hat unit vector. And again, these are tangent basis vectors, which means that they can vary in my space. So here's r hat over here, and here's theta hat over here, right? Okay, cool. So now, right, all that we have to do to determine dr, well, this is just the product rule, right? So we're going to have some dr in the r hat direction plus r dr hat, right? The only problem is we don't know exactly what dr hat is. But remember, just like in the last video, we can always figure this out if we rewrite r hat in terms of Cartesian coordinates, right? Because we know that the change in a Cartesian basis vector like dx hat, this is always going to be equal to 0, right? Which is, extremely useful. So let's go ahead and do this real quick. So if I have dr hat, which is really d cosine theta x hat, plus sine theta y hat, right? Then this is just going to give us, right? We just expand this out very quickly. We're going to have minus sine theta d theta x hat plus cos theta d theta in the y hat direction. And again, there are these terms that are going to contain, just like the product rule, like a dx hat times some stuff and a dy hat times some stuff, but dx hat and dy hat are just going to be 0 because those are constant basis vectors in our, in our space. So that's really nice and easy. So now if I pull d theta out of here, right, minus sine theta x hat plus cos theta y hat, right? Well, this guy here, this was our definition for the theta hat unit vector, right? And so now we've come up with dr. So really this is going to be equal to, right? We have our first component already, so dr r hat plus r times d theta theta hat, right? Plus r d theta theta hat. All right, great. So we have dr. All right, so next we're going to expand dt out using, the multivariable chain rule. In other words, if we know that t at the end of the day is just going to be a function of our coordinates r and theta, notice how the perspective is just a little bit different, right? I'm saying that the temperature is a function of our coordinates as opposed to a function of our position. Really, it's like potatoes, right? But I'm saying this to emphasize that you could write out dt with the multivariable chain rule as partial t partial r dr plus partial t partial theta d theta. Right, and I think it's very important that I distinguish the multivariable chain rule from what we're trying to do, right? Just to emphasize, we're trying to relate the change in temperature to when we move in a displacement vector dr, right? This guy here tells us if I just change each of my coordinates one at a time, first I change r, then I change theta, what's the corresponding change in temperature? But, moving in some direction dr is not the same as just changing r and changing theta some amount, right? Because again, we can see that this dr vector is actually some, slightly more complex, nuanced, form of my coordinates. Okay? But now, with these ideas, we're able to all put this together. So, I'm going to just plug in for each. First, I plug in for dt, so I have dt, dr plus dt, d theta is equal to gradient of t. I don't know what this looks like, but it's dotted with drr hat plus r d theta hat. And we know, as I said before, right, this has to be some kind of vector, right? So this is going to have some component a in the r hat direction plus b in the theta hat direction, and we just need to see what a and b are, right? And so if we expand all of this out, it's just a dot product, right? And kind of the rule with dot products, if you dot product two of the same unit vector, that's going to give you 1, okay? And so we have a dr plus b r d theta, just like this. Great. And now we're saying that this is equal to dt dr plus dt d theta. All right, now can you read off what a and b are, right? So a, look at this, a is just going to be dt dr, and b, right? B is going to have to be equal to 1 over r dt d theta. You see that? And so the Nabla operator acting on t, or in other words, the gradient of t, is equal to dt dr r hat plus 1 over r dt d theta in the theta hat. Or, Making this even more clear, let's pull just the Nabla part out. This is kind of our gem that we've been looking for. So forget the t, and we're left with d dr r hat plus 1 over r d d theta theta hat. And there we go. Now we have the Nabla operator in polar coordinates. And this is extremely useful. Like I said, not just for analyzing scalar fields. Of course, in scalar fields, we get the gradient, which, we talked about a bit here. But we can also use this when discussing vector fields. So this is a very useful tool that we just extracted. If you enjoyed this video, let me know in the comments and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.